Hi, welcome to the final lesson in arc sectors and angles and circles. This is lesson 12, tangent kites. So we'll start off with a quick starter today. Pause the video and have a go at the two questions below. Remember, where you see the pencil and paper icon to do the work into your jotter, and you're allowed to use a calculator here. Okay, let's look at question 1. So here we have been told CD is a tangent to the circle and we've been asked to find the size of angle COD. Now, if we have a tangent to the circle, then we know straight away that we have two right angles at the base of the circle there, where the tangent touches the circle. This creates two right-angled triangles. In order to find COD, we need to find angle Q. So we add the 90 and the 32 together to get 122 degrees. Take that away from 180 and we get 58 degrees for Q. We also need to find angle R, so we follow exactly the same process. So add the 90 and the 47 from the triangle on the right hand side and take the answer of 137 away from 180 and that gives us 43 degrees for R. So angle COD is the total of Q and R, so we add these together and we get 101 degrees. If we look at example 2, again we're told AB is a tangent to the circle, so straight away we can fill in the right angle at vertex A. Now we have a right angled triangle where we know two sides and we're being asked to find the length of the radius, which is AC. So we can see from the triangle, we're being asked to find the shorter side of a right-angled triangle, so we would use the subtract version of Pythagoras. Filling in our values, we get AC squared is equal to 42 squared, take away 29 squared, which gives us 923, and we remember to square root that, and AC is 30.4 metres. Okay, let's have a look at today's lesson, tangent kites. So today we are going to be looking at finding angles and lengths formed in tangent kites. By the end of the lesson, we should be able to know the properties of tangent kites and apply the properties of tangent kites and use them to find the unknown angles and lengths. Let's have a look then. So we have a circle. So remember, a tangent is a line that touches the circumference at one point only. So two tangents can be drawn from any point P outside a circle. So for example, AP and BP are tangents. Remember, tangents make right angles with radii at the point of contact. So we can see from the diagram that AP is equal to BP, that's by symmetry, and OA is equal to OB because they're both radii. So this gives us a tangent kite. The quadrilateral, remember that's a four-sided shape, OABP is a tangent kite. Please copy the next slide into your notes jotter. So we have a tangent kite here and we can see that it has two right angles. That's what makes the tangent kite special from a normal kite. The line of symmetry creates two identical right-angled triangles. So if we split the quadrilateral down the centre, we can see that creates two right-angled triangles. The line of symmetry is therefore the hypotenuse of the right-angled triangles. Now, we need to remember that three angles in any triangle add up to 180 degrees, but also four angles in any quadrilateral equal 360 degrees. Now that makes sense because this quadrilateral is two triangles, so that's two 180s. So here's an example. AC and BC are tangents to the circle. Calculate the size of angle BOA. Now straight away, if we're told we have tangents, then we can fill in the right angles at the vertices A and B. We're going to use the property that 4 angles in any quadrilateral equal 360 degrees. So to find angle BOA, we add up the 3 angles that we know, the 90 plus 90 plus 44. That gives us 224 degrees. And we will take that answer away from 360 degrees. So that gives us a final value of 116 degrees for angle BOA. If you look at a next example, so a slightly different tangent kite, but the same sort of idea. AC and BC are tangents to the circle. We want to calculate the size of angle ABC. So this time, we know that AC and BC are equal. So this creates isosceles triangles in this diagram because of the dotted line. In which case, we can take the 98 degrees away from 180 to give us 82 degrees, and if we half that value, that gives us 41 degrees at the elbows of the isosceles triangle. Now the next thing is we know that BC is a tangent, so that means it creates a right angle at the point of contact. So we have a right angle at B. We can use this fact then to work out angle ABC by taking 41 degrees away from 90, and that gives us 49 degrees for angle ABC. This time we're going to look at an example involving Pythagoras. So here we have a circle where point C is 50 centimetres from the centre of the circle. The tangent AC is 40 centimetres long, and we are being asked to calculate the area of the circle. Now to calculate the area of the circle we use pi r squared, so therefore we need to know the length of the radius OA. We've been told in the question that AC is a tangent, so straight away we can fill in the right angle at vertex A. So therefore we have a right angled triangle AOC with the right angle at vertex A. This means we can use Pythagoras. Now we know the hypotenuse. Remember we said in an earlier example that the dotted line, the line of symmetry, is your hypotenuse. So we know this. So we need to use the subtract version of Pythagoras. If we put in our values, we get 50 squared take away 40 squared, which is 900. So OA is the square root of this, which is 30 centimetres. So now we can use pi r squared to work out the area of the circle. So putting in our values, the area is pi times 30 squared, which is 2,827.4 square centimetres. Now it's your turn. So just like the last lesson, if you go to posts or files on Teams to get today's exercise and answers, make sure you complete the questions into your class jotter. Remember to show all your working and make sure your answers have appropriate units. And then at the end, check and correct your work, please. Thank you.